All right, so let's go ahead and begin. So there's a bunch of stuff on each of the tables. One of the things is the graded activity from last time. Then I also put, I can find it correctly. These Otter diagrams, I think I put 8 and 8, figuring 2 for each person because we're going to go over some data path and control signals again for 3 instructions. One of the instructions is already on Canvas, but 2 of the 3, in fact, the first 2, I don't have on Canvas. So that's why I printed out the hard copies that way in class. You can follow along and you can fill it out as we go. So yeah, we're going to start off looking at the data path and the control signals for 2 instructions that we haven't done before. And then we'll get to a 3rd instruction that's a load instruction. And we'll see why a load instruction requires 3 clock cycles instead of 2. Yeah, I mentioned a few times in class that all our real instructions, again, all you have to worry about as far as the microprocessor processing of a real instruction, right? There's 30 some odd real instructions. Well, the majority of those real instructions take 2 clock pulses to process the instruction, but load instructions require 3 clock pulses. And we'll see why that's so. Okay, so that's basically the first part of the class. It's going through some more data path and control signal diagrams. So 3 more instructions. And then the second part of the class is looking at timing diagram for a program. So I have an example that I'll go through that's up on the board. It's on the overhead there, or the projector. And then the activity. Okay, I sent an email to everyone. Okay, that there's going to be another graded activity during today's class. And that activity has to do with you generating a timing diagram from your sample program that you're using for hardware 6. Okay, so I'm going to go through an example, and then as an activity, we'll go through another example. And that example being the one that you need for your hardware 6. Okay, because there's no doubt that you're going to have to troubleshoot your hardware 6. Okay, it's not going to work the first time. So, to prove that your hardware 6 works, you have to look at the timing diagrams from the simulation that you get from Vivado. Okay, well, you're manually going to come up with this, so you know what to look for when you're looking at the actual timing diagram that Vivado generates. And you're going to see that the timing diagram, what you see on the timing diagram comes directly from the data path and the control signals on your diagram for each instruction. So if it hasn't been apparent by this time, it should be apparent, or it should become apparent by the end of today's class, that the data path and control signal for each instruction, it's not only important for you to model your control models, right? Your control FSM and your control decoder, like we talked about last time. But it's also very important to have those diagrams that understand what your timing diagram is supposed to look like. When you go to show that your auto is working, and also when you have to troubleshoot, try to find out what's wrong. Okay, so data path control signals for all the instructions. I mean, it's just very important. Okay. All right, so we're going to start now. You can see I drew what's on your diagram, the Otter architecture up here, just what we need for these 3 instructions. I didn't include the branch address generator or the branch condition generator because they're not needed for these 3 instructions. And then, of course, we have the control unit modules that are supplying the outputs, right? The CSU FSM is supplying our read enables and our write enables, and our control decoder is supplying our mux selects, like we talked about. Okay, it's not showing, but again, it's on your piece of paper. So we're going to start with this instruction here. So again, this instruction, I do not have the data path and control diagram on Canvas. So you may want to use one of those hard copies I provided and just follow along with what I do here. Again, I'm going to use red for data and the blue for control, just like we did on previous diagrams like this, okay? All right, so let's start with this instruction here. What instruction is this? So again, like most classes, it would be good for you to be looking at the instruction manual. If you got your computer, you can look on your computer. I don't think anyone made a hard copy like me, but or your tablet, it would be good be looking at this as we go through it. So what kind of instruction is this? It's SW. All right, it's a store word. See, we haven't done a data path and control signal for store command. So this is our first store command, the store word. Okay, so looking at the instruction format here, what is this telling us? It's T2. Like I'm looking at the form of the instruction, SW, the form tells you what source 1, source 2, and what the immediate is. So what is this here? Is it the destination register? Let's see, I'm looking at my detailed instruction. Which one? Yeah, it's register 7, employee store. All right, so in the form of the, instruction in the detailed description, what do they list it as? It's either going to be RS2, RS1, RD2. Yeah, RS2. And then as you said, what register is this? Is it Neil? Yeah. You said the register, what was the register for T2? Yeah, so this is the alternative name for register 7, right? So put that here, okay, but that will come confusing. Okay, how about in parentheses here? What's this? RS1. Then S0 is the alternative name for which register? And I think I put on every bench, I put the page that shows the alternative names. And which one is it? Register. Okay, and then what's this 0 in front of the parentheses here? It's an offset, and in the form of the instruction, it's called a what? Immediate. And then what type of immediate is this? Remember, immediates have a type, right? We have the 5 different types. Which type is the immediate for a store? S type. Yeah, this is S type. Okay, see, before you go ahead and you fill out your diagram, you should fill out this information, right? Because we got to know what is the source registers. We got to know whether we have an immediate. Now, this instruction doesn't have a destination register, but if it did, that would be useful to know also in order to do our diagram. Now, also, we're given contents here. Okay, we're told the contents of T2, which again is register 7, is hex 66. And the contents of this register F0, which again is register 8, is hex 6000. Okay? All right, so let's go ahead now and let's fill in the data path along with the control signals. And just like we did previously, right, with all our other instructions, we start at where the address of the instruction to be executed is, right? So we start at the output of the program, right? Again, program counter. It's probably the 15th time I said this in class, right? The output of the program counter is providing the address of the instructions being executed. Okay, so that's where we start. Okay, so that address of the instruction to be executed is going to be here at address 1 of our memory module. Now remember the memory module, it has real memory, right? That's made of the code segment, the data segment, and the stack, right? The instructions are in the code segment. So now what do we have to do here in order to get the instruction to appear at DL1? Like, what do we have to do? Yeah, we need a read enable to be enabled. Which one? I have 2 here. Which one is it? Yeah, read enable 1. Okay, so when read enable is a 1, it's an active high, and it's also what? Active high is what else? Synchronous. Remember, the asynchronous reads are the red button. Okay, but here, these are synchronous. Okay, so it's not enough just. Is that the diagram for the? Yeah, yeah, that's why I provided them, because this instruction is not on campus. Okay, the diagram for this instruction is not on campus. So yeah, I would recommend filling it out as we go along. Because once I'm done with this one, I'm going to erase it and then do this one that's also not on campus. Okay, but this third one is on campus. So that's why I gave 2 sheets instead of 3. And the last one, you'll be able to look at Canvas. Okay, but getting back to this, remember, since this is a synchronous read, it's not enough just to have the enable activated, right? It's not enough to have this 1. It's got to be 1, and then you need a 0 to 1 transition of the clock. So once this becomes 1, the next 1 to 0 transition of the clock, now the instruction to be executed will be at 1. Okay, does that make sense? See, I'm going over that again because you'll see the effect of that on the timing diagram later. Okay. All right, so now we have the instruction at the output of DL1, right? And it goes over to our reg file. So with these 3 inputs, with this instruction, what do we care about? Do we care about address 1?
Yes.
Yeah, why do we care about address 1? Because what in the instruction tells us to care about it? We have an RS1. Okay. That matters. And in fact, what is the data going to be on that address 1 input? It's going to be an 8. Right? Because that's the address of register 8. See, this is just an alternative name, right? This doesn't have the address. This gives you the address, the actual register number. Okay, so there'll be an 8. Okay, does address 2 matter? Yeah, because we got an RS2. So that matters. That matters. And what's the data going to be on that input? 7, yeah, because register 7 has address 7. Does right address matter for this instruction? No, why doesn't it matter? Yeah, we don't have a destination register. So again, there's going to be data there. You know, when you look at your timing diagram for your otter, and if you look at that address, there's going to be some data there, some number there. But for this instruction, it's not used. Okay. Okay, but what other piece of hardware do we have to be concerned with for this instruction? Because what do we have here? We have an immediate, so the immediate generator matters for this instruction. Okay, and it's an S immediate, so it's the S output here where we're going to have this value of 0. Okay, so we'll have a 0 here, and that S, as you can see, goes to the MUX engine. Like we said, the immediate value is 0. Okay, we also have RS1. RS1 is where, let's see, RS1 is F0, so RS1 has contents hex 6000. And so right here, you'll have hex 6000. And then RF2, that's the output here. We'll have hex, what is it, hex 66. The path for that hex 66 coming up. But let's look at this here. Because what is this instruction going to do? Going to store what?
It's going to add the immediate to whatever's in.
Right. It's going to add these 2 together. So it's going to take this 0 and add it to 6000 hex, right? Because we got 6000 hex. So it's going to add these 2 together and then what?
We put it in X7.
Put what in X7?
6000.
Does it store the address?
No, it's certainly
Right, it stores the data at this address. So it's gonna take the hex 66 and put it into register 7. Okay, because see, again, you gotta look at what the instruction tells us, right? SW instruction stores, oh, I'm looking at the wrong thing here. Oh, actually, there's a mistake in the description because it says SW stores a half word, but it stores a word. In memory, at the address formed by assign extending 12 immediate value and adding it to the contents of source register RS, the word is then stored in register RS2. Okay, so it's taking the data at this address and putting it into this register. Okay. All right, so it's got to add these two together. So to do addition, right, we need the ALU. So what do we need this ALU sort A to be? So that we can take the hex 6000 and add it to our S immediate value. Right, we need that to be 0. Right, because that will put the data at input 0, which where our hex 6000 is, that will put that at the input of our ALU. And then how about ALU sort B? What do you want this to be? What is it? A 2, right? Because see that S immediate goes into input 2 of our sort B months. So this needs to be 2. Okay, so now I have the hex 6000 here, I got the 0 here, we're gonna add them together. So in order to have the ALU to add, what do we need to do? What's going to determine what operation this ALU does? The ALU fund, right? So that's where you look at the table, and what do the 4 bits have to be to add? Yeah, all zeros. Okay, so that means we'll have the results here. So it's just going to be a hex 6000. Okay. Now, RS2. RS2 goes up and around. Okay, so this goes all the way. The D into a memory model. And then so here goes all the way. Oh, did I follow the wrong line? Oh, there it is. This line that goes into address. So you see the result of the ALU, that's the address. And RS2 here of the reg file, that's our data. So that's going to put that hex 66 into address hex 6000. And what's the significance of address 6000? That's what? Well, remember, real memory is made up of code segment, data segment, and stack. So yeah, it's real memory, but what part of real memory is address 6000? It's the first word address, if you will, of the data segment. If this was an address to an input device, or well, actually be an output device in for storing. Say if it was the 7-segment display that has address 11,00040, well, then that's what this address would be. Okay. So when you're storing data, whether it's to the data segment or whether it's to an output device, it's these 2 inputs of the memory module that matter. And it's going to determine the address of where this data is going to go, where it's going to get stored. So prior to today, we hadn't talked about those 2 inputs in the memory module, and that's because these 2 inputs don't come up unless, well, you'll see it also comes out for a load, but in this particular case, for storage. If we're stored, these both are relevant.
So 66 is going into data into
Yeah, the data is hex 66, and that's going into the address 6000 that was determined by these being added together. Okay, now we're not quite finished because we also have to get ready for the next instruction, right? So we need the program counter to advance to the next instruction. So also part of the data path for this instruction would be this. And we're not doing any jumping or branching here, right? A store command doesn't branch or jump. So we're just going to go to the next instruction in the program, which is for an address away, like we've talked about many times. Oh, we forgot one thing here. What did we forget? We forgot one thing here because what do I need in order for this data to actually get written, right, to the address that we have, the 6000 address? What do we have to enable here? Yeah, just write enable. Write enable 2. That would have to be a 1. Yeah. Okay. Okay, but how about over here? What do we need PC source to be? 0. That will get the data at the input of our program counter. And then what do we need PC rec to be? A 1. Okay. So I think we didn't miss anything. Let me just double check to make sure there wasn't something we missed. Does everybody agree with what we have here? I don't think we made any mistakes. It looks like we have it all. What's that? What about the reg file? This instruction doesn't have an RD, so we're not writing to the reg file for this instruction. Right? When you're writing to the reg file, you would have a destination register in your instruction. Yeah, so here we're writing to an address in the memory module. Okay. Did you guys have a question?
I would just call it the structure example of SW.
Yeah, we're doing this instruction. Okay, so any other instructions before I erase what's up there? I'm going to erase what's up there before we start this instruction.
So 80 is the 600 or
this has the hex 6000. That's the address. And like we said before, that's the first address of the data set. So this data, the 66 hex, would go into the word address of 6000. Now, if you were storing that 66 hex to the 7-segment display, well, then this address would be 110040. But whatever address is here, that's where it's going to store. Okay, any other questions? It's okay if I erase what's in red and blue and start over? Yeah. Take a minute. Just bear with me. Now that was a store word. Do you think the data path would basically be the same for store byte and store half word?
Would you have size?
Yeah, the only thing that would be different would be the bit for size here. Remember, these 2 bits for the store and also the load instructions determine whether it can be byte, half word, or word. So if you look at the details description, you'll see that for word, I can't remember. Well, we can look real quick here. Let's see, for word, what bits are they again? 13 and 12. For word, it's 1, 0. 13 is 1, 12 is 0. Half word, it's 0, 1, and byte is probably both zeros. Where's store byte? Yeah, store byte, those 2 bits are both 0. So that would be the only difference. Everything else, the red lines and the blue numbers for the control signals, they're always. So that's why I don't have a store byte or store word for an example, because it would be the same as what we just did, except for that 2 bits for the size. So, you know, when you're doing your diagrams, right? In fact, if you did the diagram right now, then yeah, you got your diagram, you can just write somewhere. Only difference for store byte and store half word is, you know, what we talked about. All right. So I drew these lines too close together. Oh, one thing that this reminds me about. See how I wrote this mux input going to 0, and I wrote these mux inputs going to 0. I did that because these go to outputs that deal with interrupts. You know, like this goes to, I think, 2 outputs of the CSR module, which stands for Control Status Register. And that module, you know, it's just relevant for interrupts. And since we're not covering interrupts, you can just connect those into 0, like in your code. And same thing with this mux here. So that's why you see 0 there. Yeah, sorry about drawing these lines so close together. I should have thought about that when I drew it. Plus you have the diagram. So if anything's not clear up here, just look at the diagram and that should clear it up. And you know, if you have a question about it, please absolutely. Did I get everything? Do you see anything red or blue that I missed? I think I got it all right. Okay, thanks. All right, so let's move on to this. Okay, we did this one. Okay, let's look at this instruction, this AUIPC. So let's see, what instruction is that? What does this instruction do? Everybody got their detailed description? Yeah. Yeah, it says it adds an upper immediate. We saw upper immediate somewhere else. Where did we see upper immediate in a previous instruction? Yeah, there's an LUI, right? A load upper immediate. And do you remember what that instruction did? Yeah, it shifts the immediate 12 bits to the left. That's what they mean by upper. Okay. So this one here, this AUI APC, I'm not sure exactly what the acronym stands for, but let's see, what does it say? It says this instruction sums an immediate value and the current value of the program counter and stores the result in a destination register. The 20-bit immediate value is left shifted 12 bits in location. And the lower 12 bits are cleared, in other words, made to be 0. The instruction only modifies the destination. Okay, so what's this P1 then? Looking at the form of the instruction, that's the destination register. And T1 is which register? Is it 6? That's what I have. Everybody agree? It's 6, X6. Oops, not there. Because what's 80? That's an immediate. And what type of immediate does this instruction have? It's U-type. Very good. It's U-type. Okay, so we're gonna, also for this instruction, let's see, I wrote it down here. Let's assume, I'm just picking some number, some number divisible by 4, right? Because it's an address to an instruction. But I'm just saying that we're at the instruction at address 24. So the output of the program counter is 24. And again, I just picked that number out of a hat. But again, it's going to be divisible by 4, like we talked about. All right, so we start again at the output of the program counter. Right, that's where the address of the instruction to be executed is at. What do we want here? I want read enable 1 to be 1. Once that becomes 1 at the time of the next 0 to 1 transition of the clock, the instruction at that address will now be at the output of DL1 of the memory marker, right? So that's where the machine code of this instruction AU IPC is going to be. Okay? All right, so now we're at the reg file. What matters at the reg file? Does address 1 matter? Address 2? WA? Right, so that's the address of the destination register. Right? We have a destination register, so it matters for this instruction. And what's the data going to be at that WA input? It'll be 6, right? The P1 is register 6. Okay, does the immediate generator matter for this instruction? Yeah, because there's an immediate. It's 80. Right? It's a U type. Okay, so immediate generator matters. And it's a U type. So that's where the 80 is. That U type goes up to, where is that U type? Okay, now what else matters? Because again, what is this instruction doing? What else matters? Instruction sums an immediate value and current value of the program counter. So you see, program counter matters. Right, the output of the program counter where our 24 is, right? The address of the instruction. That comes over to this mux. Right, so we want to add those two together. Right, and the ALU is the only thing that adds, things from registers and things from like the program. Okay, so what do we want ALU source A to be? That to be 1. That will connect this output of the immediate generator, this 80, that will connect it to source A of the ALU. What do we want ALU source B to be? We want that to be 3. Right, that will put that 24, right, the present program counter output as ALU source B. Then we want the ALU to add. So what do we need here? All zeros. So what are we going to have at the output of the ALU? What number? It's going to add these two together, right? The 24 and the 80. So 104. And we want to put that into a register. So this is where the reg file matters, right? We want to take that and write it to this destination register T1, which is register 6. So what do we want this to be? 3. Okay, that would put that data right there at the WP for the reg file, and to make it actually put the data into register 6, what do we need? Okay. Yeah, you gotta have the reg right for 1. Okay, now also we need to get ready for the next instruction. So what do we want over here? 0 for PC source, right? Anytime you go into the next instruction, if you're not jumping or branching, you just go into the next instruction, you want PC source to be 0. And then also, what do we need? 1. 1 for PC. Okay, so let's see. Did we miss anything? I think we got everything. Just double check. Does everybody agree with what we have? We didn't miss any blue numbers or, yep, it looks good. Okay, so does everybody agree with this? Any questions? If there's no questions, I'm gonna erase and we're gonna get to really the focus of today. Okay, because you're gonna see. Where does the left shift by 12 happen? Oh, I'm so glad you asked that. It happens right here. You make it happen when you did immediate generator, because if you look at the U type, the let's see, 0 through 11, and focus are all 0. So it's taking whatever the unit is, shifting it up by 12 bits. So yeah, if you were to look at LUI, remember we did load upper immediate, you would see the same thing. With the load upper immediate, you're not adding it to anything. With the load upper immediate, whatever you have here directly goes to the ALU output. Okay, this one, the difference is you're adding what's here to the PC. That's really the only difference between these two. I'm glad you asked that question because I wanted to point it out again. Yeah, the 12-bit shift happens here. Okay. So any other questions up to this point? Everybody's good with these two? Because these two instructions, just like all the previous instructions, right? I don't know, if you count up all the instructions we've done in class, it's probably around a dozen or so, right? Because we did like 6 and then, I don't know, like at least 3 branches and a couple of jumps. So probably right around a dozen or so, okay? All these instructions that we've done in class require 2 clock cycles, okay? A fetch and an execute, okay? Like we talked about last class. But what you're going to see here is that if you have either like a load word or a load byte or load half word or, you know, load byte unsigned, load byte, or load half word unsigned, load word unsigned, any of those, okay, any of the loads except for the LUI. Okay, the LUI we did and saw that, you know, there's 2 clock cycles set for that one. But load word, load byte, and load half word along with the unsigned version, they require 3 clock pulses, okay? And you're going to see why, okay, when we do the data path. Okay, so, but before we get to that, any questions on this one before I erase everything?
Is there a way to describe specifically where the, like, along this instruction, where the 2 clock cycles happen?
Well, when we get to the timing diagram, I think that will be clear. But real quick, okay, just real quick, but we'll see in more detail when we get to the timing diagram. For all the instructions that require 2 clock pulses, not only these 2, but all the others, right? It's basically a clock pulse to get the instruction here. Okay, that's called fetch. And then it's a clock cycle for the instruction to actually execute. So the data path from when the instruction is at the out1 to whatever the finality is, whether you're writing to a destination register or whether you're writing to like a data segment or writing out to a, you know, an output device, that's all 1 clock cycle. That's called the execute. Okay, but what you're going to see with this load word coming up is that a fetch and an execute is not enough. Okay, and you'll see why coming up. Okay, all right, but all good that I can erase what's up here. Alrighty, so if I miss anything, let me know. Now, this load word instruction, you know, the data path and control signal, it's on Canvas. Okay, so you don't need to actually, you know, do the diagram here in class unless you want to. Let's see. Here. Get them all? think I got everything now. Let me just draw in those black lines up here. Actually, I'm gonna get rid of this one because we don't need this one for to make it a little clearer. You know, that connection here to the MUX, that's when you have a link like a jump, you know, like a JEL, you know, that's for the link to store the return address. So anyway, just to clear it up a little bit. Like I said, I apologize for not giving more room there because I wasn't thinking of it. There's this. Okay, I think that's better. All right, so we did this one. Okay, so now we're on this load. So what does this instruction do? Let's look at the detailed description. LW. What does LW do? Very similar to SW, isn't it? One's a load, one's a store. So what is this instruction doing? You have the detailed description. Load the word from memory into the specified destination register. So where's the destination register here? T0. Okay. And T0 is what register? Alternative name for which one? 5. And then how about S0? What's that? X8. And is it a source 1 or source 2? Source 1. And then what's the 0? It's immediate. And what type of immediate do we have for load word? I type, right? Again, you all know where to get it, right? You just look at the detailed description, see right underneath instruction format, it has the type, I type. Yeah, so this is an I type. Okay. So it's going to take, well, it's going to add this offset to whatever's in this register S0, right? Then it takes this as an address and it'll put the contents at this address into this register. Right? Everybody agree? Okay, so let's start where we always start. Oh, I accidentally erased this line. Oh, it's right in my email. I accidentally erased that one. Sorry about that. Okay, so we're going to start at the output of the PC counter, just like program counter, just like we've done before. That's where the address of our instruction is at. Okay, so what do we want here to happen? Right, read equal 1 equal to 1. Okay, now we have our instruction at the output, the out 1 of our memory module. So what's going to matter as far as the reg file inputs go? Do we care about address 1? We got an RS1. And what's the data going to be? It's going to be 8 or 5. 8, right? That's RS1. So 8 is going to be here. Does address 2 matter? No, there's no RS. Does WA matter? Yeah, because we got a destination register. Okay, and what's the data going to be here? 5. Okay, immediate generator matter? Yeah, because we have an immediate, so it matters. Okay, and it's the I type output where we're going to have a 0. Right? That immediate 0. And then Okay, what else do we have here? We have an RS1. So RS1 here will have whatever the contents of register 8 is. Right, so S0 register 8. We didn't make up any number, so it's just whatever the contents are. So we can write that as just like X. We'll just put X8. Which again, this is the same thing as S0. So this is contents. Contents of S0 or X8. Okay. All right. So what's going to happen next? Oh, by the way, let me just point out, this is on Canvas too. I actually made a mistake originally on Canvas. Like I showed this as an S type instead of an I type, but I made a note. So when you look at the diagram on Canvas, you'll see right above the diagram, I put in bold, important correction. Immediate should be I type, not S type. Okay, so I just wanted to point that out. You know, what I have here is the correction to what's on here. Okay, but what do we want to happen now? What are we going to do here? Yeah, we add these two, right? We add the immediate along with our contents of S0. So what do we need this ALU source A to be? Need that to be 0, right? Right, that's going to connect what's on input 0, the mux, to the source A input of the ALU. What do we want the source ALU source B to be? A 1. So that's going to connect the immediate right here on input 1. The source B, these are going to get added. So we'll have the result of that as well. In order for them to get added, what do we need ALU funds to be? Need that to be all 0. Okay, good. And then this is going to come up. Go right here. And then let's see. Oh, my mistake. That's not true for this instruction. For this instruction, into the load instruction, this is going to come over this address. Okay, because just think, when we use load instructions, this address is typically what? The address of what? Like in your programs, when you were using like a load password or load word or load byte. Yeah, like some sort of input device, like that's usually a switch. Okay. So you see, that's why this output here, because this is an address, right? It adds these two together, then it uses this as an address. So that's why this is going over to this address. Okay, I was incorrect when I do it. Okay, we'll see where this comes up in the next second. Okay, so now we're reading from this address. So since we're reading from this address, because remember, this is a load instruction, right? So load instructions like a read, right? Remember, a store instructions like a write, right? So since we're doing a load, which is like a read, we want read enable to be enabled. Okay, so we want read enable 2 to be a 1. Right? For our store instruction, right? When we were doing a store word, remember it was write 2, that was 1, right? Because that was, you know, store instruction. This is a load instruction. So that's why this is enabled for load, and that's enabled for store. Okay. So now, here's the problem. The problem is that this read, right, our reads for our memory module, they're synchronous, just like this write to the reg file. So remember, we want to take the data at this address and put it into this register, right? Register 5 of the reg file. Well, on our second clock edge, this old data is going to be put into register 5 before the data at address 2 is at DL2. So you see, that's the problem. And that's why load instructions need another clock edge, because we need a clock edge to put the data at this address at DL2 before we write it to the registry. See, with 2 clock edges or 2 clock cycles, we would just take the old data. See, this data hasn't been updated to what's at this address yet.
So do we just overwrite the data, or do we like actually delay and wait for the new data to be there?
Well, it's just that we need another state. Like, instead of just fetch and execute like we have for all the other instructions, if we have a load instruction, we're going to have to add a third state. Okay, because we need another clock edge. Because with just 2 clock edges, whatever destination file we specified in our reg file, it won't get the data at this address. It will get the data that's at this DL2 that was there before. Like, it's getting like old data. Okay, so you see, that's the difference with any of the load instructions, you know, load word, load byte, load half word, in the previous instructions, right? Because the previous instructions didn't have like this extra module, if you will, that synchronized before we got here.
I guess my question is, why not just have a delay instead of like a whole extra state?
Well, that's essentially what a state does, right? I mean, it delays it by a clock cycle. But your FSM is working every state in a state diagram is a clock cycle. Yeah. So essentially, you know, when you say delay, that's what we're doing by adding a clock cycle. You know, for that one instruction, we're delaying by a clock cycle before the data we're interested in gets written to our destination register. Okay. You know, I think of all the things in this class, I think this is one of the trickiest things to kind of, you know, have it sink in. You might have to think about it a little bit more. I know when I first ran across it, you know, I have to think a little bit more about it. Also, when you look at a timing diagram, I think it starts to make a little bit more sense too. Okay, but that's the issue with load instructions that comes up that's different than other instructions. You need that extra clock pulse to get the new data here before you write it into the register in the reg file. Okay.
Is it also because like memory is synchronous?
Right, yeah. Exactly. Because it's synchronous, that's why we need the clock, right? Yeah, with synchronous reads here, where here we have asynchronous reads. So that's why that's a valid point. Do you have a question, Kevin?
Could we just bypass the synchronous that way in asynchronous? That way it'll be another clock edge.
You know, that's a great question. Remember, Dr. Hummel designed this memory module, and that's something that I thought about, and other people have mentioned, but I haven't asked Dr. Hummel. I would assume Dr. Hummel is a very smart person. For those of you that know him, he was a very smart guy. I would assume there's got to be something else that requires it to be synchronous. Because yeah, if this was an asynchronous read, then you wouldn't have to worry about the process. So I don't know. That's a great question. I will definitely ask him and see why they were. I'm sure there's a reason. I just don't know what it is. It has to do with something, how this is designed, and you know, maybe something else in it requires it to be synchronous. So yeah, it's a great observation. Any other questions up to this point?
So the accuracy here is the output.
Correct. Right. The contents of this address would be here at EF. And then that's what we're putting into the destination. So you see, what we're going to have to do let me, I know it's probably kind of hard to see with my podium here, but, you know, I kind of wrote out the problem, right? So this is a more, you know, concise way of saying what I just explained. And then, you know, the solution is to add a state. So, you know, the result, if we didn't fix this, the result would be old data saved instead of the data we want. The old data saved instead of correct. So we're going to have to add a state to our state diagram for our FSM. And this added state, we call write back. And you see, we only want to go to the state if it's a load instruction. If it's not a load instruction, right? We're going to execute. And if the load not a load instruction, well, we just go back and fetch, right? It's, you know, it's not a load instruction. Again, it only requires 2 clock cycles. But if it's a load instruction, we're going to go to write back. And then after write back, you go back to execute. Okay, now, there's one more key thing. Oh, actually, we forgot to finish this off here. You know, with going to the next instruction. Let me just quickly put this up here. So that's all going to be the same. But you see, there's one other thing you got to keep in mind, and that's for all the instructions other than the load instructions, when you're in execute, because all other instructions except the load instructions require only two clock pulses. Well, when you're in execute, you would make your you would make your PC write equal to 1 because, you know, 2 clock cycles, you're done with that instruction, you want to move on to the next one. But when it's a load instruction, do we want PC write to be a 1 when we're in execute? No, because if it's a load instruction, we're not done with that instruction until we're in the write back state. Okay? So when you have a load instruction and you're in the execute state, you don't want this to be 1 yet, right? Because you don't want to move on to the next instruction. You want that to be 0, right? You don't want to move on to the next instruction until you finish with the load instruction. So when it's a load instruction, you got to make sure that the PC write is 0 in the execute, right? Which is unlike all the other instructions, right? And all the other instructions that require 2 clock cycles, you would want this PC write to be 1 because to those instructions, you would be done after 2 clock cycles and you want to move to the next instruction. But for a load instruction, you don't want PC write to be 1 until you get to write back. Okay? So in the execute for a load instruction, PC write is 0, and then when you get the write back, you make it a 1, right? Once you're done with the write back state, then you're done with the load instruction, right? And you want to move on to the next instruction. Does that make sense? Okay.
Load instructions are the only ones that go that extra state.
Correct. Yep. So load word, load byte, load half word, along with the unsigned, right? Because there's the unsigned ones too. Those are the only ones that require 3 clock cycles. Yeah. Okay, and then just to finish this, I mean, you know, in the write back, you would also, you know, want to make it 0, and that's when you would actually write the data to the destination register. You know, this is happening during the write back. Where would the old data components? Say that again. Where would the old data? Well, the old data is just whatever was there. Like maybe, no, maybe you had some previous load command. You know, again, all these outputs and inputs, they all have data at all times. right? So it's not like if something's not being used, there's nothing there. Now, it could be all zeros, it could be a mixture of zeros and ones, all ones, whatever it may be. It's just that when you're interested in using it, that's when it matters.
LUI is exempt.
Well, think about the data path for LUI. Did the load upper immediate involve the memory module at all? No. So
Same thing for load immediate.
well, load immediate's a pseudo command. It's a pseudo instruction made of two other instructions. I think it's made out of LUI and ADDI, if I remember right. And remember, as far as designing your modules, right, we only care about the real instructions, right? Because if your otter is executing all the real instructions, it will execute all the pseudo instructions, right? Because pseudo instructions are either multiple real instructions or sometimes, well, most of the time, they're a single real instruction just with a special value somewhere. Okay, I think it would be a good point here to take like a 5-minute break because we've gone over an hour or just about an hour. And when you come back, I'll show you the timing diagram and then you can do the activity after that. Okay?
Sure, but I mean,
okay, so let's go ahead and get started. Is everybody back? It may be, depending on where you're sitting, it may be hard to see what's on the screen here. So, I mean, if you want to move over, you know, especially people like in the back corner there, I mean, if you want to move over, just move your seat and come over here so you can see better. Okay, because the activity that I'm going to have you do directly relates to what we're going to talk about with this timing diagram. And I'll leave this up when we work on the activity. How about, can you guys see? The table right here, you're kind of at a bad angle, but can you see okay? I mean, you can come up here. Don't be afraid. Okay, so like I said, you know, doing the data path and the control, you know, signals that you need for each instruction, it's not only important for when you design your control modules, right, with the FSM and decoder, but it's also important to be able to understand what a timing diagram should look like. So this is what you're going to be looking at in Vivado when you do Hardware 6 and also when you do your final project to make sure that your design is actually running correctly, okay? So I just have a sample program. I just have a sample program that I'm using for this timing diagram, and I put that sample on your table, okay? Everybody should have this handout. It says program for lecture timing diagram. Okay, so that program is what this timing diagram is for. Okay, I don't think I had enough for everyone. Yeah, I put 4 of them, so everybody should have that. And then the other program, you know, the other hard copy with the other program, that's the sample program for Hardware 6. And that's what your activity is. That, you know, once I explain this timing diagram based on that program, you should be able to take the Hardware 6 sample program and generate a timing diagram just like I did. Okay? All right, so let's look at what we have here now. Up at the top, it's just showing all the states of our FSM. So it starts with fetch, then execute, fetch, execute, fetch, execute. This program doesn't have any load instructions. So all the instructions in this program are 2 clock cycles, fetch and execute. And that's the same for your Hardware 6. Okay, your Hardware 6 sample program, right? Those 6 instructions, there's not a load instruction. So they're also going to be all 2 cycles, fetch and execute. Now, an assumption here is that we've already gone through the initial state. Okay, so remember, in the initial state, that's where we set PC reset to 1. So we start at a program count address of 0, right? Because again, that's where the first instruction is always located. Okay, so, this timing diagram starts with this output of this program counter being all zeros, right? Address 0. Okay, so when we've gone through the data path and control signal diagram, what do we always make read enable 1 equal to? A 1, right? Because we need that enable in order for the instruction to then appear at DL1. Okay, well, look, in our timing diagram, during the fetch state, this column is the fetch state for address 0. Well, look, this is memory read enable. I know it's hard to read here, okay? But this is set to 1. So now with that set to 1, at the time of the next rising edge of the clock, which is right here, the instruction will be at the output of DL1 of the memory module. Now I wrote LUI here just for shorthand, but really what's there is a 32-bit machine code, right? So you see, in the fetch state, that's when read enable is made a 1. But then this output, DL1, goes to the instruction at the time of this rising edge of the clock, which is the beginning of the execute state, right? So this read enable is set to 1 during fetch. This instruction will appear at DL1 right at the beginning of the execute state, right? Because it took that clock edge, because it's synchronous, right? This is a synchronous read. So in addition to these being a 1, right, we also need a clock edge for the instruction machine code here to be a DL1, right? So that's why you see the instruction here. Does that make sense? Okay. Well, now look at all these values during the execute state. Like, for example, ALU has a value. Here is the write address. Okay, for this LUI instruction, the write address was 8. Here's the U type value. Here's what the mux for the reg file has to equal. Here's the reg write value. Here's the ALU source A value. Where do all these values come from? The ones that I wrote in red and the ones I wrote in blue during this execute state. PC write, PC write equals 1 there. PC source equals 0. Where did I get all these values from? Say again? Well, some of these values are coming from the decoder, but I'm just talking in general, like where do these all come from? What do I need to have in front of me to know what these values? Yeah, the diagram, the data diagram and control signal, right? During execute, these values that you see during execute, they come directly from what we talked about when we did these diagrams. See, again, that's why you need the diagrams for each instruction, right? To know what's supposed to happen at what time, okay? Now, the key thing is, for all these instructions, whether we're writing to a reg file or, whether we're writing some data at an address, well, that data isn't updated until the beginning of the next fetch cycle, right? Because if you're writing to a register in the reg file, since it's a synchronous write, well, you make the values for that write to happen during execute, but then the actual data doesn't get written to that register until the next rising edge, since it's synchronous. So you see, like for this LUI instruction, see how the address, 6000 in this case, doesn't actually get written to the register until the beginning of the fetch cycle, the next instruction, right? And again, that's because we have synchronous writes. So if you set an enable to write during execute, the actual write of the data into the register doesn't happen until the next state, the next fetch state. Okay, that's probably the number one reason why people have difficulty with timing diagrams is, you know, they're looking at an execute state and they're like, oh, it's supposed to write to this register. And they're looking at the execute state and they see the old data in that register and they're like, hey, it's not working. Well, it's working. It's just it's synchronous. So it doesn't get updated until the next state because it needs that edge of the clock. Right? So just always keep that in mind that when you're writing to something, a register or whatever it may be, or an output device, you're not going to see that new data until the following fetch state. Does that make sense? Now, like I said, these are all two thought cycle instructions. The only difference, and I have an example on Canvas, I didn't print it out for class, but there is an example on Canvas that shows a program that has a load instruction. I can't remember which one it is. It doesn't really matter because all load instructions, it's going to have an extra state write back. So the only thing you would see different is if you had a load instruction, you'd have fetch, execute, and then write back. All right, and then it would go to fetch again and just keep repeating. And like I said, what's different with the write back is what your PC write is, right? Because for any load instruction in the execute, you want your PC write to be 0, right? Because you don't want to move on to the next instruction yet until you're done with the write back. So that's really the only difference in a timing diagram with a load instruction. Okay? So, I don't know, is this enough where you think you could do that sample program? I'm going to leave this up here so you can use it as a reference. I think, you know, maybe I'm wrong, but I think timing diagrams are fairly straightforward as long as you understand the data path and the control signals for each instruction. The tricky thing, like I said, is when something gets written to, the data gets updated, the fetch cycle after, or the fetch state after the execute. Right? It doesn't happen during the execute because it's synchronous. Remember, all our writes are synchronous. We don't have a single asynchronous in this order. Everything that gets written when it's written, it happens on the clock edge. All the reads are synchronous except for the reg file. These two reads are the only asynchronous reads. Everything else is synchronous. Okay, so do you have any questions or do you think you can tackle the activity? Because the activity, like I said, is to take, let's see, where is it? Does anyone have the, yeah, thank you. Yeah, the activity is to take this sample program. This is the sample program for hardware 6. So you want to take this program and do exactly what I did here. In fact, some of them are the same, like LUI, ADI, SLLI. Let's see, I don't have an SLT up here. You have exclusive where I got an OR, and then branch if equal, I got a branch if not equal. So some of the instructions are the same instructions that I have in this example that I have up here. Now your registers might be different, you know, your numbers might be different, but the instruction is the same. Okay. All right. So work on the activity again. We'll go by tables, just, you know, one submission per table and, you know, no more than 4 people. So keep it to 4 people. If you have more than 4 people, you know, move somebody to a table that doesn't have 4 people.
Keep track of it.
Right. Yeah. Just like I did, you may have to write additional inputs or outputs here. So see, like I did.
I don't know, bro.
I think I put this on Canvas also. So I'm pretty sure I put a PDF of this on Canvas.